So we are starting with probability, okay? And I kind of like to use this chart in terms of what is probability, the likelihood of an event occurring. So you have 0 out of how many chances it's impossible of happening. Even like flipping a coin, it's 1/2. Certain it happens all the time. Okay, so that's what we kind of look at. There's two types of probabilities. Okay, there's theoretical. Okay, which is the probability that is determined on the basis of reasoning. What should happen? Okay, so you're assuming you're given 4 choices. What is the chances of choosing a red? Right, 1 out of 4, whatever it is. Experimental is actually what's happening. So if you do trials, 20 trials, and you landed 4 on red, then it's 4 out of 20. Okay, so experimental is 5 appears 140 times. This is what it would look like. Theoretical is 1 out of 6. Okay, experimental is actually happening, and theoretical is what should happen. So anytime we are describing probability, and the notation is important because when you see the P in front, that stands for probability, and that puts in your mind that you should express it as a decimal, reduced fraction, or a percent. Okay, so probability is either as a percent, as a fraction, or as a decimal. Okay, and that is an indicator with the P in front. Okay, if you were to write an answer, because this happens so many times, where they are looking for probability, but you just give a whole number, that's not what probability means. Okay, the probability has to be expressed as a percent, fraction, or decimal. Typically, a lot of the time, we're going to see the reduced fractions. Okay, we're going to give our answers as a reduced fraction form. So, for example, probability of winning the lottery equals, this is what it stands for, probability of winning the lottery. Outcomes of probability, simplified fraction, decimal, or percent, which I just mentioned. So, for example, if you had rolling a 5 using your own die, okay, so what is the probability of rolling a 5? Well, theoretically it's 1 out of 6 chances of rolling a 5. Now, experimentally, say if we rolled it 20 times, how many times we get 5 would go 5, whatever number, out of 20, okay? That's experimental. Theoretical is what happens 1 out of 6, and experimental is what actually does happen. So let's try some examples. Assuming you're tossing 1 coin, find the probability of the following. What is the probability of landing on heads? David? 1/2, okay? And we're going to express it as simplified fractions. Probability of landing on tails? Gotcha. 1/2, good. What is the probability of heads and tails? Look here, yes. Look at your faces. Is that possible? All right, but is it really possible of happening? No. You never know is right, but typically landing on heads and tails is impossible. Okay, how about probability of heads or tails? Yep. 2/2. Good. Excellent. Just certain. 2 out of 2. Excellent. Yeah, David. You could write 1 because that's simplified there. Okay. Okay. Assuming you're rolling 1 6-sided die, find the probability of the following. Write your answer as a fraction. Don't worry about percentage, just write it as a fraction. Go ahead, you guys. Give that a try. Okay. What is the probability of rolling a 5? Jax? 5 over 6. Careful. Yeah, Kip. 1 out of 6. Okay. What is the probability of an odd number? Eleanor? 1/2. It was 3/6. Deuces to 1/2. Excellent. Probability of odd or even? Yeah.
6/6.
Yep, good. 6/6, which is 1. Excellent. Probability of the factor of 6. Riley? 2/3. Good. 4 to 6, which is 2/3. Factors of 6, 1, 2, 3, and 6. Okay. How many of you got all 4 of those correct? Good. Okay. So Spotify has your playlist of 200 songs, 45 of which are Taylor Swift songs. Determine the probability of your shuffled songs playing a Taylor Swift song.
It's 45. The 45 obviously are included within the 20.
Okay, what's your initial fraction? What do we got? Kate? Good. 45 out of 200. What does that reduce to? Go ahead, Kate. 9 over 40. Excellent. Good. How many of you guys got that? Perfect. Good. All right, so now you guys are going to try in terms of a dozen cookies. Go ahead. So, out of a dozen cookies in a cookie jar, so how many do we have in total? 12. Good. Okay. Total. Excellent. Okay, 9 are chocolate chip, 3 are sugar. Determine the following probabilities. Find the probability of choosing a chocolate chip cookie from the cookie jar. Pearson, what do we got? 3/4. 9 out of 12, which is 3/4. Okay. Suppose that your friend selects a cookie before you and chooses a chocolate chip cookie and eats it. Now calculate the probability of you choosing a chocolate chip cookie after your friend. Go ahead, Kip. 8 out of 11. Why is it 8 out of 11? Jaden. Perfect. Excellent. How many of you did get 8 out of 11? Perfect. So that leads us to 2 things. Distinguishing how 2 events are, okay, between independent versus dependent. Okay, independent events, the outcome of one event doesn't affect the outcome of another. Okay, so for example, if I chose a cookie, then put it back, the total resets, right? However, the second event, the second problem that we just saw, that a cookie was eaten, right? So the total lessens, therefore it does affect the outcome. So that's a dependent event, okay? So when you are or have some sort of replacement, keyword replacement, okay, then that's still an independent event because the total resets. Dependent is where it changes, okay? One affects the other. The first outcome affects the other. It is important that we differentiate between independent and dependent events in order to calculate probabilities. So, we're looking at these 2 scenarios. Number 1, the marching band is holding a raffle at a football game with 2 prizes. After the first ticket is pulled out and the winner is determined, the ticket is taped to the prize. The next ticket is pulled out to determine the winner of the second prize. So event 1 is winning the first prize. Event 2 is winning the second. Are these events independent or dependent? Yes. Careful. It's okay. It's all right. Jaden? Perfect. Okay. These are dependent events. Okay. After someone wins the first, so after someone wins the first, technically they can't win the second, right? Because their name is pulled out. All right. Okay. So the first winner has to happen first before the second. All right. Now if we look at the next one, you are choosing a marble from a jar. There are 6 red marbles, 4 blue, 3 green, and 3 purple. Each time you select a marble, you look at the color, then put it back in the jar. So, first event, choosing a red marble first. Event 2, choosing a red marble second. Are these independent or dependent? Riley? Independent. What was the key word? Independent because it was put back in the jar. Okay? All right. So I want you guys to try 3 and 4. Okay, 3 and 4, determining if they're independent or dependent. All right. Number 3, event A, picking up an ace in a standard 52 deck, replacing the card in the deck, and then picking up a king. Independent or dependent? Yeah, Catherine. Independent, why? Good. Independent. Because of replacement. How about number 4? Earning first place in a track meet, then earning second place. Yeah, Noel. Why? Perfect. Excellent. Very good. So if 2 event, yeah.
For number 3, would it even matter to put it back because it's a different card? Like, you're picking up an ace and
Yes, because the probability changes.
Okay.
Okay. The total lessens. Okay. So if we look at if 2 events are independent, like we've seen, okay, then we can figure out the probability of the following. So keywords here. If you're looking for the probability of event A and event B, you are multiplying those 2 together to find the probability of both occurring. Okay, so event A and event B, you will be multiplying. We're going to see that in a few minutes. If you're looking for event A or B occurring, okay, if you find the probability of either event A or event B occurring, you will be adding. Okay, so and means you're multiplying both events together. They're both separate probabilities, or you are adding. So if we look at it this way, here's example 1. Given you are rolling 2 6-sided dice at a time, determine the following. Leave your answers in simplified fractions. So, rolling the first die and rolling the second, are they independent? Yes, they are. Why? Yeah, Eleanor. Right, nothing's changing. Rolling one die and rolling another, They're two separate events, okay? So now that we determined that they're independent, what is the probability of rolling a 2 on a die or rolling a 4 on die 2? So what is the probability of rolling a 2 on die 1? Aiden. 1/6. And or means, are we adding or multiplying? Adding. What's rolling a 4 on die 2? What's the probability of that? 1/6. So when we add those guys together, what do we get? Okay. 2/6 is 1/3. Okay, so when you're looking for probability of both occurring, you are adding. So now we look at B. What is the probability of rolling a 2 on die 1 and rolling a 4 on die 2? So keyword and, what are we doing? Multiplying what together? 1/6 times 1/6. What do we end up getting? Yep. 1 out of 36 chances of that occurring. Okay. Now we look at C. What is the probability of rolling an odd number on die 1? So what's the probability of rolling an odd number? 3/6. I'm going to leave the denominator as is. Or rolling a 6 on die 2. So or means what? What are we doing? Adding. And what's the probability of rolling a 6? 1 out of 6. So we're adding here. What do we end up with? Yeah, Kaden. Perfect. Okay. What is the probability of rolling a factor of 4 on die 1 and rolling a factor of 4 on die 2? So what is the probability of rolling a factor of 4? Yep. 1/2. So 3/6, which is 1/2, and we have it the same thing for die 2. Are we adding or are we multiplying? Multiplying, good. 3/6, so this is 1/2 times 1/2, which is 1/4. Okay, good. Try example 2. All right. So you're choosing marbles from a jar and putting them back. So right then and there, that determines that they're independent because you're putting them back in after each pick. There are 6 red marbles, 4 blue, 3 green, 3 purple. How many in total? Yep. 16 in total. Good. All right. So what is the probability of selecting a red marble first and selecting a green marble second? So how would I set that up? Let's see. Christian, how would I set that up? Good. Excellent. How many of you did get that? Good. And then if you were to reduce, whatever it might be, did you get 9 out of 128? Good. Excellent. Okay. What is the probability of selecting a blue marble first or selecting a purple marble second? Let's see. Eliza, how your setup was. Yep. Excellent. And what you got? Excellent. Good job. in your OR, so you are adding 4 out of 16 plus 3 out of 16. If you guys haven't noticed, I typically leave it with our total given instead of reducing, because we don't want to then find a common denominator if we needed to, or go back. All right? So what is the probability of selecting a blue marble 3 times in a row? So what are you doing here? Yeah. So we're multiplying. Excellent. So there's 4 blue marbles, so 4 out of 16 reduces to 1/4. So we have 1/4 times 1/4 times 1/4. And what do we get? Yeah, Kaden. 1/64. Excellent. Good. How'd you guys do with that? Pretty good? All right, awesome. All right. And one of the last things for today. Okay, so if 2 events are dependent, we actually do this all the time, believe it or not. If 2 events are dependent, we must look at the probability of event B will occur under the condition that event A already happened. Okay, so this is where you would see without replacement sort of thing. All right. When thinking of dependent events, we need to think about how the total denominator changes. So you're going to see this notation. Probability of B given that A has already happened. Okay? So keyword here, given, means it's talking about something called conditional probability. All right? So if you're looking at this example, a drawer contains 10 masks. Okay? That's our total. 3 black, right? 3 black, 3 patterned, 2 bright colors, and 2 white. Every day during the first week of school, you wear a mask and then put it in the wash to clean. Calculate the following and leave answers as a reduced fraction. All right, so we have here probability of selecting a pattern mask given that you already selected a white mask. Okay, does that make sense? Probability, and you guys are going to write this in words, probability of selecting a pattern mask, probability of selecting a pattern mask, given that you have already selected a white. Okay. Probability of selecting a pattern mask, given that you already selected a white. Okay. Now, how would I rate that? How would I evaluate it? Okay. 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 So think of it this way. All right. So in total, how many masks do we have? 10, right? If we already chose a white, how many are we down to? 9. So wouldn't that be my denominator, right? Now, out of those 9, what is the probability of choosing a pattern? 3. So all we did here is we already chose the white, so we're subtracting 1 right off the gate. Okay? We already chose a white mask, so now we're down to 9. Now we look at a 9, how many of those are pattern? Does that make sense? So this had to happen first before we chose the pattern. Yeah. We already know that they. The reason with dependent events is the first event, which actually in this notation comes second, if that makes sense. This event has to happen first before this one occurs. Okay, does that make sense? So 3/9 reduces to 1/3. So that just stated the probability of choosing a pattern mask given that you have already chosen a white mask. Sense? Make sense? Okay. Now, looking at B, probability of selecting a pattern mask, okay, given that you have already chosen a white and a pattern, okay? So I want you to jot that down in words. Probability of selecting a pattern mask, given that you have already selected a white and a patterned mask. Okay. All right, so probability of selecting a pattern mask, given that we have already selected a white and a pattern. So with these two already occurring, how many are we down to? 8. Both of you, good job. So we're down to 8, okay? Now, how many pattern in total do we have? 3, right? But one was already chosen, so what are we left with? 2. So 2 out of 8, which is 1/4. Does that make sense? So basically you chose a white first, then a pattern, then your last pattern. So you're getting rid of 1, you're getting rid of 1. Okay? So these are your first 2 events, and then your pattern happened last. All right? Are we okay? All right, let's try the last 2. All right. Probability of selecting a black mask, given that you've already selected 2 black masks. Hayden? 1/8, okay? Because we already selected 2 masks in total, so we're down to 8. However, we have 3 black masks in total. 2 are already chosen, so we have 1 left over. Does that make sense? All right, try the last one. Probability of selecting a white mask, given that you've already selected 2 other white masks. Mhm. Jack's already said the answer already. What do we think? Yeah? Why not? Right, so since we already chose 2, we're down to 8, right? But then there are only 2 white masks, so we can't choose a third because there's nothing left over. So 0 out of 8, there's no white left over. Okay? So we went through our basic probability, theoretical and experimental. Okay? We went through independent versus dependent. All right? Now, this last thing that we're going to do before you guys get to some practice is going to set us up for next class. Okay? So, I need some honesty here. How many people do we have in class? Let's see. 26, I think. 4, 8, 10, 18. Yep, 26. All right, so we have 26 in total. By raise of hands, how many of you are sophomores? Keep your hands up because I don't know off the top of my head. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, okay. 18. 18 are sophomores. Okay. How many of you are Warner House students? I'm a little biased for that. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Okay. How many of you are both sophomores and Warner House students? 1, 2, 3, 4, 5, 6, 7. Okay. How many students are neither sophomores nor Warner House? Okay. 1, 2, 3, 4, 5, 6. Are you in or no? Okay. So what are we? 5? 5? Okay. Okay. So we're going to use this information, all right, to fill out a Venn diagram. Okay. So we're going to we have sophomores and then Warner House. Okay. How many of you are familiar with a Venn diagram? Know what they are, right? Okay. So we have 18 students that are sophomores. So this whole circle will equal 18. Okay. How many are both sophomores and Warner House students? 7, right? Okay. All right. So 7 goes in the middle because it's both sophomores and Warner House students. Okay. So sophomore and Warner House, hold your hands up again. Sophomore and Warner House, so 7. Okay. Now, keep your hands up. Okay. The rest of the sophomores, hold your hands up. Okay. So how many others are just sophomores then? 11, right? Yep. 11 are only sophomores that are not Warner House students. Okay. So then, if we have 7 who are sophomores, okay, and Warner House students, so those 7 again, sorry you guys, raise your hands again. Okay. How many are Warner House students? Only. How many are just Warner House students? With those guys that are already up. Just Warner House. How many more? 3, right? Because we have a total of 10 Warner House students here. 7 of them are sophomore and Warner, so there must be 3 of you, which is Riley, your Warner House, right? Charlie. Who else is Warner House?
Only Warner House?
Just Warner House and Kate. Okay. 3. Okay. So we have 26 in total. 26 students in total. How many do we have in this Venn diagram already? 21. Okay. So how many are neither? 5, right? Yep. 5, which we already calculated.
Where would you put
Here.
that? Like on the outside?
On the outside, but still in the box. Okay. So you guys see how we did that? It's kind of hard with the hands. I like when you stand up and kind of do this. But what this shows is we're going to get to this next class. Okay. But what we did is we first started off with, we have 26 in total. So this whole Venn diagram, every piece of it has to equal 26 in total. Okay. The whole Venn diagram has to include every single person. Okay. There's 11 that are only sophomores. Okay. That are only sophomores. Not including Warner, only sophomores. Okay. There are 7 that are both sophomores in Warner House. Okay. There are 3 that are only Warner House students. okay, not sophomores. There are 5 students that are neither Warner House or sophomores, okay? So what we did is we subtracted, like Jack said, 7 from the total number of sophomores, making this whole circle equaled 18. How many are Warner House students? This whole circle equaled 10. We can't count 7 twice because then we'll be over our limit. That's why we subtracted it here. Okay, does that make sense? Okay, what we just did was filled out the Venn diagram. Now, what is the probability of selecting a Warner House student? Yeah. Yeah, go ahead.
Is it 10 over 21?
Over,
21? Because, like, the 5, I think that you can select 5.
it's everybody in total.
But, like, even if they're on one, still count. Oh, still count.
Everybody, yep. So 10, we'll reduce later. 10 out of 26. Probability of selecting a student who is a sophomore who is not a Warner student. Perfect. Okay. Probability of selecting a student who is neither a sophomore or a Warner House student. Perfect. Good. All right, you guys. So that's where we are going to end today. Okay. This whole experiment is going to lead us into next lesson. All right. I'm going to give you your practice.